Welcome back, everybody. This is the third and final part of my three-part lecture series on AlphaGo. In the first part, we introduced Monte Carlo Tree Search, and in the second part, we described AlphaGo's implementation of it. In this third part, we're going to be focusing on the deep learning networks that AlphaGo uses in conjunction with reinforcement learning and Monte Carlo Tree Search. If you haven't seen those first two lectures, I highly recommend it. All these lectures have been building on each other, and it might be tough to understand some parts without watching the first and second part. AlphaGo's neural networks assist Monte Carlo Tree Search with two tasks. The first is predicting expert human moves from a specific board position. This happens in the expansion step when creating a new node to initialize the prior probabilities for different moves. The other task is predicting the probability of winning from a specific board position. This happens as part of the evaluation step in conjunction with traditional Monte Carlo rollouts. The first pair of policy networks are trained from a dataset of human Go games. These networks predict the probability of an expert playing certain moves. This supervised network is duplicated and used for reinforcement learning. It plays many games against former versions of itself, improving over time. The reinforced network plays against itself to create a dataset of positions, which is then used to train the value network that predicts win probability. So this first network that we're going to be talking about is the supervised learning policy network. This is one of those that gets the prior probabilities for a set of actions from a given state. So this first neural network task is to predict human expert play from a given board position. The researchers at DeepMind did this with a 13-layer policy network using a dataset containing 30 million positions. Features included the current board state, move history, and other Go-specific information. The deep learning classifier was able to achieve an accuracy rate of 57%. Doesn't seem very high, but it's actually pretty good. The previous industry standard was 44%. In Monte Carlo Tree Search, the results from this classifier are used to initialize the prior probabilities P when we expand a new node. These prior probabilities serve as a roadmap to identify promising moves. An accuracy rate of 57% is actually enough for the network to beat advanced amateur players by itself. And this is a network where a small difference in training accuracy goes a long way as far as win rate goes, as you can see on the graph on the right. But the consequence of that is to get higher training accuracy, you're going to have a cost as far as computation time goes, and that could be an issue if you're trying to do many iterations of Monte Carlo Tree Search in a certain amount of time. So there's a trade-off there, as with everything. So like I said, the policy network is very accurate at predicting expert moves, but it is also very computationally expensive. So because of that, we want to use a different network for those policies versus the policy we use when we're rolling out and doing those Monte Carlo simulations. Because the evaluation step of Monte Carlo Tree Search relies on having a simulation strategy that picks moves very quickly, because you want to do as many simulations as you can, as quickly as you can. So the network, the policy used for that is a less complex linear softmax classifier that sort of trades accuracy for time. It is less than half as accurate as that supervised learning policy network, but it's over 1,500 times faster. So that's a trade-off that we're able to make because we do want these rollouts to be as fast as possible, and also we can kind of compensate for the lack of accuracy in the rollout with the value network, because if you remember, in our evaluation stage we do a blend of those two valuations. So then our next step is to improve that supervised learning policy network that we trained off of the human expert positions. And we do that through reinforcement learning, a process where the network plays games and receives rewards or penalties based on its performance that it then uses to update its weights and to learn. So the reinforcement learning policy network repeatedly plays against randomly sampled older versions of itself. We don't want it to play against the same version of itself over and over again, because that would lead to overfitting, as the same moves would be chosen each time. And so when we run these self-play games against older versions of itself, the game is played until it reaches a terminal state, where we give a reward of 1 for winning and -1 if we lose. And then that reward is used to update the network's weight at each time step or move. So when they created this network, they had it run in self-play for about a day on, I think it was 8 CPUs. And that got the supervised learning policy network, and it improved on it to where it better predicted good moves, strong moves that would lead to wins. So like I said earlier, in the evaluation step of Monte Carlo Tree Search, in addition to rollouts, we also use a value network to predict the probability of winning from a board position. And this is important because, like we said earlier, that rollout policy isn't very accurate, so we supplement it with this value network. DeepMind used its best reinforcement learning policy network to create the data set to train the value network, as it was their best model of strong play. They recorded game states and outcomes from self-play with both players using the same policy. Initially, they created a dataset including every game state from a given game. Successive states were very similar and were all given the same outcome label, as they were all from the same game, and this led to an overfitting problem, as it would get all these similar game states from the same game and kind of not be able to generalize to more game states. And so their solution to this was to only sample 1 board position from each self-play game. This fixed the overfitting issue, and they ended up with an accurate assessor of win probability. This network is used in the evaluation step of Monte Carlo Tree Search as part of the Q-value calculation. Thank you for watching this 3-part series. Once again, I'm going to have my sources for this episode in the description. If you have any questions, feel free to drop them in the comments. I'll try to answer to the best of my ability. Thank you for watching. I hope you have a great day.